The last time they did a Chandrayaan, that was Chandrayaan-2, and that was in 2019. And at that time, I was a scientist at Indian Space Research Organization, a full-fledged one as well. I still remember the night at which they were going to have the landing, the moon landing of Chandrayaan-2. I was actually on a bus returning from Sriharikota, which is the launch pad of ISRO. We were working at that point in some GSLV Mark II launch that was going to take place next year early, which never happened that early because, COVID pandemic happened, and ultimately the F-11 launch, I think that was the launch vehicle that we are working on, happened significantly like 6-7 months later. I don't remember the exact date, but that's what I was returning from. Like our team, I was in the engine team. I was working in earth storable rocket engines. To those who are not from technical background, even from the propulsion background, understand that the fuel that is used in those rocket engines are liquid in room temperature, and also those kind of engines you'll see everywhere. You saw it in the launch of the Chandrayaan-3, which, to be more specific, was done with GSLV Mark III. Mark III has a twin Vikas engine, and these fire right after the S-200 fires on the ground level. It fires a little bit above the ground, but still like well inside the atmosphere of Earth. So I don't want to get too technical too fast. In a basic manner, I want to explain what this whole mission is about. So what I'm going to do is, first of all, compare the timelines of Chandrayaan-2 and Chandrayaan-3, and it is very similar, right? So they launched it in July 2019, Chandrayaan-2, and this time in July 2023 they launched Chandrayaan-3. What is the exact reason for that? Well, when it comes to orbital mechanics, a lot of things comes into the play, like when are these two celestial bodies the closest. For example, you might have watched that movie Mission Mangal, right? And if you watched that movie, you know that they are talking about a thin bracket, a narrow bracket that they get to launch it. That's where Earth and Mars are in the closest range, so that they invest the least amount of energy. And in a similar manner, I do not know the perfect orbital mechanics, but all of these orbits, none of them are circular, right? They're all elliptical orbits. So when it comes to two elliptical orbits, there will be a narrow bracket. Maybe you'll get two, maybe you'll get only one. Depends. For that, you'll have to study both the orbits of Earth and Moon. Here, the orbit of Earth does not matter as much because Moon is orbiting Earth itself. Another reason why they are doing it in July might be that August 15th is the Independence Day, and they would like to do something patriotic somewhere close to that. So you'll see that there are a lot of dates, and the events, if you look at it, it just says that first orbit raising, second orbit raising, third orbit raising. So it's like you cannot blame a lot of people to think that you launch a rocket and it lands on Moon, right? It's a straight path, you go over there. But the thing is, the way that we move on Earth, like if you have to go to the grocery store and the grocery store is straight ahead of you, you drive your car straight, right? And when you're looking at, oh, Moon is there, Earth is there, so I'm going to drive my rocket straight. But that's not how it works, because when you're talking about gigantic celestial bodies and compare that with the small spacecrafts that you have, then the gravitational influence is humongous, and it is going to be extremely difficult for any spacecraft, and we are going to say spacecraft and not rockets, because spacecraft would be the ultimate payload which is going to move through space and time. So you can think about Chandrayaan-3 as a spacecraft as it looks on the screen right now, right? And this is something that is going to actually reach to Moon, and this is the payload of the GSLV Mark III launch that you saw. All of that effort, tons and tons of energy for just this payload, and this payload is not directly go to Moon in a straight path. It is going to orbit Earth multiple times, and what we are trying to do is kind of get away from the gravitational field of Earth. When it comes close to Moon, it now also has the gravitational effect from Moon, which is significantly lower than the gravitational field of Earth. But as when it is about to land on moon, it is much closer to moon as compared to Earth now. Now the gravitational field of moon is more dominant. And that's when it enters the gravitational field of moon, and now it starts an orbit around the moon. So our objective for Chandrayaan-3 over here would be to reach higher and higher orbit of Earth so that it ultimately touches the gravitational field of moon, gets caught by it, and starts having an orbit around moon. So that is why you can't have a straight path. Like if you want to have a straight as an arrow line between Earth and moon, the amount of energy that you are going to need is going to be monstrous. It's not even physically possible. You know, the problem with launch vehicles, it is always a complicated design because, well, I want power to leave the surface of Earth so that I reach an orbit. For that, I want to put a lot of energy down below, right? It's basically just Newton's third law, push and go up. When you're in space, it's more conservation of linear momentum than Newton's third law. Basically, for layman term, you can say that I'm going to push against the Earth, so I'm going to have an explosion. And this explosion, by the way, ladies and gentlemen, is measured in gigawatts. The power plants that you're talking about, thermal power plants, nuclear power plants, their energy is like 500 megawatts. But these launch vehicles, all of a sudden, an explosion of gigawatts happens on the surface and just throws whatever is on top of that explosion away from the surface of Earth. This energy is a problem because if you want more energy, you'll have to have more fuel. And what is going to give more fuel? The one which is causing an explosion. So if you are having more fuel, you are having more weight. So if you're having more weight, you'll need more fuel. And if you're having more fuel, you'll need more weight to be lifted. So it's a very complicated science that rocket scientists have to always work around to find that weight of fuel that will just balance and throw it with a velocity and acceleration. So it's difficult to have a launch vehicle which actually reaches the orbit, basically. So that's why they say it's how difficult can it be? It's not rocket science, right? Rocket science is really the most complicated science that you can think of. What we are trying to do over here is reach an orbit and then raise that orbit, right? Now we want to reach closer and closer to the gravitational effect of moon. So over here you can see that when it comes to Chandrayaan-2, they did a launch on 22nd July. Then around 2 days later, they did their first orbit raising maneuver. So like I said, any of these orbit when an object is influenced by another gigantic celestial body is going to be an ellipse. This is actually one of the Kepler's law. Some of you guys might remember studying this in middle school. So it is going to be an ellipse, and that means that it is going to have two centers. Ellipse has two centers. And one of these centers is going to be the object around which it is having the ellipse or around which it is revolving. Now, that means that if you look at this ellipse, the object will be at one point closest to the object around which it is revolving. At the one point, it would be farthest. And that closest point is called periapsis, and the farthest point is called apoapsis. Now what I want to do is basically raise the farthest point, right? So that it ultimately reaches moon, it gets caught in that moon's gravitational field and creates an orbit around moon. I'm going to fire rocket engines at periapsis so that my apoapsis raises. So what we are basically doing is adding energy to the orbit. And if you are going to add energy at the closest point, the farthest point is going to increase. That's where the physics that you see on the surface of Earth is going to be far different than the physics that you see in orbital mechanics. Because in Earth, what happens is that if you want to have a turn, you are going to turn right away. If you want to go faster, then you are going to accelerate. But over here, if you are going to go faster or if you want to go further, then you have to put energy a little bit ahead of time, right? So if you're going to fire engine when you're pointing this way, you're not going to go this way. The thing is that you are in a revolution, so you fire an engine when you're going like this, but you are obviously going to go in an elliptical orbit, and all that is going to happen is that ellipse is going to become larger. Or you can think about it like the major axis. As you can see, 22nd July 2019 to 13th of August 2019, these are all maneuvers, and on 13th of August it is trans-lunar injection, right? So this is what I'm talking about. This is where it gets caught by the gravitational field of moon. Now our objective is to reduce the orbit. So earlier, to leave Earth and get caught in the gravitational field of moon, I want to raise the orbit. But when I'm caught by the gravitational field of moon, I want to drop the orbit, get closer to the moon. And ultimately, what is going to happen is your orbit is going to shrink down to a parabola. And that parabola is going to be how you are going to fall on moon or land on moon. And that's where it gets complicated, because you need to now start thrusting some energy on moon in the downward direction, so that your acceleration towards the moon is very, very low. So you're talking about like a gentle soft landing.